Hello, my name's Maddie. So glad to be here speaking with you today. Unfortunately, I can't be here live, but I'm really looking forward to being able to watch all of the talks later once it's a reasonable time zone here in Australia. So today I'm going to tell you about some work that I've been doing using the BlueTides simulation to make predictions for what we will be able to observe in terms of quasar host galaxies with JWST. So, in the local universe, there exist extremely tight correlations between the properties of a black hole and its host galaxy. So, here we have the black hole mass against bulge luminosity, velocity dispersion, and bulge mass. And so this suggests some kind of relationship between the growth of black holes and their host galaxies. We're not entirely sure what that is. And the best way of trying to understand why these relationships occur is investigating how they evolve with redshift. So measuring black holes at higher redshift is relatively easy because we've got quasars that are extremely bright and we can see out to higher redshifts. Measuring the host properties, however, is where things get a bit trickier. So here we have host galaxies in the local universe. These are two images with HST. So you can see the really bright quasar at the center, which has surrounding more extended emission from the host galaxy. So this and measuring the properties of these galaxies is quite relatively easy at low redshift, but things get much trickier when you go to higher redshifts. So here we have again an HST image of a redshift 2 quasar. You can see now that quasar emission is really starting to dominate the image that we see. And so the way that you can try and detect the underlying galaxy emission is by doing some advanced modelling. And so by modelling the PSF of the telescope to account for the quasar emission, you can basically subtract off the quasar and see what's left underneath. And so this has worked really well at redshift 2. However, if you go to even higher redshift, so redshift 6, this is another HST image obtained by the same team of a redshift 6 quasar, and you can see now that really we're just getting the PSF of the telescope and there's no extended emission. But applying the same modelling techniques, you could still hope that there is underlying host emission there, but unfortunately that is not the case. And so with our best telescopes at the moment, it is not possible to detect the rest frame UV emission from high redshift quasar host galaxies. However, we still can get some interesting information out of these kinds of techniques. So here is a study that we published earlier this year looking at a small sample of redshift 6 quasars. You can see that we, using the subtraction technique, have got stellar mass limits, and we can now place these objects on the black hole stellar mass relation. But we've only got limits. At the moment, we really would like detections. In terms of measurements, we can actually alternatively go to the rest frame far infrared. However, that's tracing the gas and the dust in the galaxies. So it doesn't tell us about the stellar properties, which is typically where these black hole host correlations exist. So hopefully things will change with the launch of James Webb next year. So James Webb, I'm sure you're all very aware, is an infrared telescope. And so what this means is that while HST can give us rest frame UV coverage of these redshift 6 quasars, we'll now be able to also observe their optical emission, which hopefully will make things a little bit easier as well. But the main exciting thing, I think, in terms of this kind of science is that with its much larger collecting area, Webb will have much better resolution, and hopefully we'll be able to start actually resolving some of these quasar host galaxies. So in this work, we're trying to address a few key questions. So firstly, will JWST actually be able to observe the host galaxies of redshift 7 quasars? Secondly, what's the best observing strategy using James Webb to observe these quasars? And so for this, I'm only considering photometric observations, just because of the way that these HST studies have been completed in the past. And then finally, what are the best quasars to target with JWST? Are some going to be more detectable than others? So for this, we're using the BlueTides simulation, making mock images of the quasars, and then running them through the observational pipeline used in these HST studies to see whether JWST will actually be able to make these kind of detections. So the BlueTides simulation is an enormous hydrodynamical cosmological simulation with a box height of almost 600 megaparsec on a site. So this massive volume means that there are lots of these very rare high-redshift quasars that we can study. Unfortunately, because of the volume is so large, that BlueTides has only been run at very high redshifts and down to redshift 7. However, at redshift 7, there are already hundreds of quasars in the simulation. And so for this work, we focus on SDSS-like bright quasars, of which there are 22 with magnitudes greater than 22.8. And so we then make mock images with SynthObs software of each of these 22 quasars, and then basically trick our observational pipeline into thinking that these are real observations. And then we can make some detailed predictions of what JWST will see. So in terms of the observational pipeline, for the PSF modelling, we're using PSF-MC, so developed by Myra Mechley in the earlier work that I showed you in the introduction. And so this is a MCMC-based 2D surface brightness modelling software, which allows you to model the image that you get from the telescope as containing a quasar and a host galaxy. Basically allows you to subtract that quasar light off and see what's left underneath. So the way these observations work in reality is we have to characterize the PSF of the telescope, and the best way that we've found to do that is by taking observations of stars. And so for this work, we actually make mock star images as well as mock quasar images. And so we pass these images through the PSF-MC pipeline and then see what we get. So for this, we model the quasar as a point source and the host galaxy as a Circic profile. And then we also run an additional model where we just include the point source quasar. Then we compare statistically these two models to determine whether the host galaxy is statistically significantly detected. So as an example, so here we have one quasar observed in both HST and JWST in the H band with an exposure time of 4.8 kiloseconds. So this left panel here is what you get when looking with a telescope. So, so it has the quasar emission and the host galaxy emission. And so we pass this through PSF-MC and it finds a best fit Circic model for the host galaxy. If you look at the residual with the quasar subtracted, we have these images here, and then in the final plot on the right, in the right panel, we have what the host actually looks like. Now, the benefit of having these simulations is that we know what the host galaxy looks like without the quasar light, and so we know directly what to compare it to. So ideally, you want this PSF subtracted panel to look like the true host panel. So running the statistical analysis, we find for this example, HST makes no successful detection, but JWST does. And so looking at all 22 of our quasars, we find that HST can detect none of these host galaxies, while JWST in the same exposure times and wavelengths can detect 10 of the 22. And so we can visualize that here. So we've got the fraction of successful detections as a function of wavelength, Hubble detecting none, James Webb detecting almost 50%. And so to answer the question, will JWST be able to observe the host galaxies? It seems a very promising yes. But can we do better than 50%? So here is an image of one of the quasars after PSF subtraction in various exposure times, so from 1 to 10,000 seconds. against the true image of the host galaxy. Now, if we look again at the fraction of successful detections as a function of wavelength, so we're considering the F200W band here, you can see that, so for 1, 2.5, 5, and 10 kiloseconds, we get increasingly better success fractions. And so in terms of the best observing strategy, it really looks like we need more than 5 kilosecond exposures to guarantee that we're getting a really large fraction of successful detections, so more than 50%. So those were in the F200W filter, but what about different filters? So we have on the top row the one quasar again in each of the wideband near-cam filters, redwood of the redshift 7 Lyman break, and then, so this is the PSF subtracted image against the true image. So what we find is the success rates here, so red for 10,000 seconds and orange for 5,000 second exposures. And what we find is that actually the longer wavelength filters have larger success rates. However, the shorter wavelength filters aren't particularly bad. It just may mean that we may need to supplement the shorter wavelength exposures with more exposure time. So finally, we also consider MIRI, which is shown here for the shortest wavelength filter. And so we find that MIRI in this filter has a success rate of less than 30%. And so longer wavelength MIRI filters will have lower sensitivity and are likely to perform even worse. So what we find is that really near cam is the way to go in terms of getting a lot of successful detections of host galaxies. So the final question then is, what kind of quasar should we target to optimize our number of successful detections? So for this, we classify a host galaxy as detectable if it's detected in 5 or 6 of the 6 filters, or undetectable if it's detected in less than 5, just for simplicity. And so we've got the black here, detected, and the white are the undetectable host galaxies. So here we have the host brightness against AGN brightness, and these histograms actually show the success fractions. And so here we see that the brighter host galaxies have larger success rates than fainter host galaxies. And so what we find is that quasar host galaxies may be more detectable if they're bright, massive, have relatively low bulk to total mass ratios, and are more extended. However, with our large error bars from our small sample size, none of these trends are actually statistically significant. So in conclusion, will JWST be able to observe the host galaxies of high-redshift quasars? The answer, hopefully, is yes. And then in terms of best observing strategies, we really need large exposure times, more than 5,000 seconds, the long wavelength filters, and near cam seems optimal compared to MIRI. What are the best quasars to target? Well, statistically, we find no significant trends. However, if you've got an ALMA image that shows really extended emission, very massive galaxy, maybe that's a good one to target. So thanks so much for listening. A paper about this is coming out soon. Please, if you have any questions, let me know via the Slack channel. I'll be sure to answer them when I wake up in the morning. And feel free to email me at the email address below. Thanks so much.